It really is a great pleasure to be here and to have this opportunity. So I chose a rather grandiose title, Information, Knowledge and Wisdom, T.S. Eliot, Science and Technology and Industrial Strategy. But I'm going to start, first of all, I think, as one should, by saying congratulations. Well done, Peter Higgs. It really is great news, isn't it? You may notice that on the stage behind me is a poster that says, research is great. This is part of the BIS campaign about things that are great about Britain and puts research right up there. And what it features is, in fact, the Large Hadron Collider, the very huge instrument that was built in the search for the Higgs. Michael Levitt got the Nobel Prize in chemistry. And he's a graduate of physics at King's. So it's really been a very, very good year for King's and for physics in particular at King's. So congratulations to all. But with that, let me just say something about titles, having got the grandiose title. And I'll introduce you to this one, Topics in Random Signal Theory. It goes back a while. It was the title of my PhD thesis some years ago. But with the confidence that comes with the passage of time, I could admit that it would be more accurate had I indeed called it Random Topics in Signal Theory. Now, you might wonder why I mention that, but the reason, in a sense, is that I'm going to touch on various topics, and I'm sure that at least for a while, if not continuously, I will appear to do so at random. But by collecting a few things together, I hope there will be some sort of underlying message. So let's start with my title, Director General, Knowledge and Innovation. It's the best bit of the job, actually. It's all downhill after the title, but we won't go on from there. But what do we mean by that? What does it encompass? Of course, I had a group in BIS, and there are three big handfuls, as I like to think of it. The research base, that is the research councils that fund project research and the like throughout the UK. The innovation directorate that helps, at least to some extent, to make sure that that research, where appropriate, is picked up and can be translated through to impact with industry and so on, with the innovation agency playing its part, that which we call the Technology Strategy Board. And then the third big handful, and you can see I'm struggling with two hands, is higher education. Brackets in England, because of course higher education is involved. But I want to focus on those three things: research, innovation, and higher education, which is sometimes referred to as the knowledge triangle. And I start with this observation. No nation can decide and sensibly set out to be good at just one of these. To be good at any of them, we have to be good at all of them. And good in this context means excellence, by the way. So one of the things that I'm really keen to do in my role is to get people to think about the completeness and coherence of the whole, whilst, of course, taking their particular emphasis as they will. So I'm going to, first of all, do a little bit of that context before diving into research and the like. So let's start with universities. What I've done here is shown three international league tables of universities from around the world, and I've chosen the top 10. And if you look at it that way, they're the one that comes out of Shanghai, the Jiangtao, there's the Times Higher Education supplement, as I refer to it, and the QS ranking. First off, they're different. You notice that different universities are differently positioned. You would think there is not too much consistency. But what I now am going to do is to colour the rectangle in which each university is, red or blue or whatever, according to the country that that university is in. And you find that there are only two colours. In the top 10 of each of those rankings, only two countries rank, the UK and the US. We can be sure that we have some outstanding universities in the UK. There are some very, very good features in our higher education system. And we could go further. I mean, I could go deeper. You would find things there. A recent ranking of the universities in the world that were less than 60 years old put the UK at the top, and so on. Even in more specialist rankings, you see that we sit up. So we have, unquestionably, something to nurture and take care of, which is a very impressive and very important higher education system. Another of my handfuls was research. And these are well-trailed statistics, but I will repeat them. With about 1% of the world's population and about 3% or thereabouts of frontier research funding, the UK produces around 8% of the scientific publications, gains around 12% of the world's citations for those publications. And if you look at the most influential, highly cited papers, then we're up around the 14-15% level. For a country with 1% of the world's population, that is pretty impressive research performance. What about innovation? Well, I think the rhetoric generally, and indeed the belief, is we're not where we need to be. And I think that is true. If you just look at this research performance, there is more to be done. But there has been progress. If we look here, this is a measure of innovation performance produced by the World Intellectual Property Organization. And in 2009-10, the UK was ranked number 11 in the world. But in successive years, it stepped up, and they currently rank us as number 3. Another ranking, produced by the World Economic Forum, that is about collaboration between universities and industry, had us as number 12 at around 2008. And in successive years, once again, we moved up to number 2. We're not still number 2, but we're in the leading group. We moved from not quite an also-ran, but certainly not a leader, to being a leader on that measure. And I don't claim causality, conditionality, but there would appear to be a correlation with some actions. Around about 2008, we formed the Technology Strategy Board as an arm's-length body from government, gave it more freedom, and as a consequence, a lot more interaction between higher education and industry, and a lot more engagement of those smaller and medium enterprises that are really thrusting to innovate. We also introduced the impact agenda to the research councils, not without some comments, but let's observe that this happened. And of course, for the research excellence framework that's coming up, once again, impact will feature. And interestingly, the Higher Education Funding Council for England took a very small slice of its core funding that it sends to universities for research and allocated it, instead of informed by the research assessment exercise, informed instead by research in those universities that is funded by industry in the UK. And in successive years, you saw a change. So I think we are in a very strong position in relation to the conditions for innovation. We're probably a bit underpowered if we're being honest about it in terms of the resources that go in, but something to be done. It's for that reason that I'm asking people, and I'm sharing this with King's this evening, but have done it elsewhere, to say, let's look at these 3 things: higher education, research and innovation, and think about the coherence and completeness. In a sense, ask ourselves what good would look like some way downstream. And my aspiration is that this would be a shared endeavour of forming a broad consensus, an 80-20 kind of consensus. We will assemble some evidence and share it. That will enable us, I think, to build a bit of a case of what good looks like, and hopefully through that process, a growing awareness that these 3 things don't sit in isolation, but we need to put them together. And that's part of my agenda and my role. And then there is something new which has come about in the last couple of years, which is in the UK we have established an industrial strategy. It's a whole of government strategy, and it's a partnership between government and industry. How do we pull things together to get maximum effect? It has a number of strands, such as important sectors, skills, technology, which is where the research bit comes in very strongly, and so on. And then in particular, within the spectrum of sectors, a modest number that are particularly important for the UK economy have been highlighted. I stressed its partnership, and one of the first things that was announced was an Aerospace Technologies Institute, a £1 billion commitment from government and industry together for activities in aerospace. And one of the things that will enable, I think, is that coupling between industry and academia and doing things at scale. I'm going to show you an example. It happens to be from where I come from, because those are the examples I have access to, of doing things at scale. The right-hand side picture is the X-48B. It's an aerodynamically scaled model of a future very large transporter aeroplane that is so different from conventional aeroplanes that is too risky to just use computer modeling and then start building. So an aerodynamically scaled model has been configured and is being flown in tests. Top left, you'll see something that's vaguely similar, as they say. Here's one we made earlier, as it were, which was in fact a postgraduate student project at Cranfield. That's what gave the capability in that institution, and indeed that was ultimately delivered to a UK aerospace company, that gave the capability to cause Boeing to come to Cranfield and say, will you do this for us? That's really quite remarkable. I mean, Boeing's job is building aeroplanes, isn't it? That's what I mean by the caliber of the higher education system, much of it through its diversity. One of the things that I think I should emphasize there, though, is responding to pace of change. So I'm going to give you a historical example, again from aerospace. This is a picture of Harold Roxby Cox, subsequently Lord King's Norton. And Harold Roxby Cox, in his youth, as a young engineer, met one of the Wright brothers, one of the first people to fly. And later in his life, as Lord King's Norton and Chancellor of Cranfield University, he awarded an honorary degree to Neil Armstrong, the first person to step out on the moon. So if you think from first powered flight by man, in the space of one career, to first man on the moon, and indeed it was some decades after that he did it, that gives you at least one sense of what I mean by pace of change. When you open the window wide, it really is quite impressive. So one of the things we need to do is to be able to cope with that pace of change. And that's an element of this industrial strategy. The so-called 8 great technologies, very important. 8 to some extent, because it rhymes with great, which is the brand, as it were. But some areas of technology that are particularly important, where there are particular opportunities, have been highlighted and given special funding. The technology strand of the industrial strategy is actually about this being well positioned to respond to change. Oh, and at the spending review, not the spending review, the annual statement last week, not a 9th great technology, but nonetheless an allocation for quantum technology, and we should probably pick up on that slightly. I think quantum is quite an interesting thing to look at. If you think of what Einstein said, quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. I, at any rate, am not convinced that God is playing at dice. Or Sir Arthur Eggington, something unknown is going on, but we don't know what. And Niels Bohr, anyone who is not shocked by quantum mechanics has not fully understood it. Or was it Rutherford? As a theory, it's incredibly beautiful. It's amazingly accurate, and it makes no sense whatsoever. And Richard Feynman said, I think it's safe to say that no one understands quantum mechanics. But that was then. That was in the early years to the middle years of the 20th century. Where do we find ourselves today? Well, probably following on Sherlock Holmes, which is once you eliminate the impossible, whatever remains must, however improbable, must be true. And maybe that's how we come to where we are today. But we find ourselves in a world of physics where quantum phenomena are widely studied, almost a truth universally acknowledged, as it were, with quantum technologies open both to fruitful further examination in science and research, but also ripe for exploitation. And it's a different world. So part of that responding to change. And this gentleman captured it, didn't he? Darwin didn't coin the phrase survival of the fittest. That was someone else. And he corrected them. He corrected them by saying, it's not the strongest of the species that survive, nor the most intelligent, but the one most responsive to change. He was talking of evolution, of course, but how true is that also in terms of countries staying up with the pace in technology? Now I'm going to talk a little bit of science and engineering and the like, and I'm going to start by talking about the way we divide it. And this is one of the ways. This is division by disciplines, isn't it? And it's a valid one. You'll have a physics department, a chemistry department, within a school, I'm pleased to see, and so on. But it can be divided other ways. Again, Rutherford, who took the view, or expressed the view, that science is divided into physics and stamp collecting. Probably a more common one is pure science and applied science, or pure research and applied research. I don't like it, because I think too easily one slips into applied as a pejorative adjective in that sense. Not a view I share. George Porter, former president of the Royal Society and a chemist. There are two kinds of chemistry, applied and yet to be applied. Actually, that's rather good for research, isn't it? All research finds its place ultimately, has its part in this complete picture of knowledge. For that reason, my personal preference is to think in terms of frontier research. And there are many frontiers that deserve to be opened, and science and research for me is more connected than divided. So science connected, a word commonly used is interdisciplinary, probably overused or misused. Very important, don't misunderstand me, but some use the idea of transdisciplinary, taking things from one discipline to another, or multidisciplinary. We work in multidisciplinary teams. Actually there, very important, is collaborative research. That's enormously powerful, including internationally. So let's emphasize the international bit just briefly. And as usual, I call on someone else. Goethe, science and the arts belong to the whole world. The barriers of nationality vanish before them. Or Chekhov, there is no national science, just as there is no national multiplication table. I think the Secretary of State for Education has a concern about whether we got a national multiplication table, if you know what I mean. Something to do with the state of schools, but nonetheless, very powerful, I think. So now, since it's the informatics, I thought I'd talk a bit about telecommunications, if you don't mind. And this was another of my titles, not my PhD title this time, my inaugural lecture some years ago when I was first appointed as a professor and a head of school. Telecommunications, from Shannon to Mammon. Shannon, the father of information theory, a paper in 1947-48 laid the mathematical foundations for all that we do in modern communications, and still absolutely current today, Shannon theory. Now, that's nice. And Mammon? Well, Mammon, of course, is the god of money, isn't it? So why Mammon? Well, the year was 1985, and we had just privatized British Telecom and introduced competition into the telecommunications in the UK, and in the United States they'd broken up the Bell system through divestiture. So competition was starting to reign. But you do have to be careful with titles. My name is O'Reilly, and there is a River Shannon in Ireland. It transpired that for many of my colleagues in the University of Wales, they thought that I was going to tell them how I had, through my career in telecommunications, escaped from the bogs of Ireland and finally struck it rich in the University of Wales, if only. But let's look at telecommunications. And I'm going to take you back. I'm old enough that I'm allowed to go back a long way, further than any of you can. The telegraph, that's where it started, electric telegraph in a way. And you can think of that as the internet of its day, in a sense. And I thought I'd acknowledge Wheatstone here, played a big part in it, and of course I'm in King's College, so why would I not? But the telegraph got going, and then Bell came along and invented the telephone. Well, that was going to make a difference. What sort of difference was the invention of the telephone going to make? Well, here was a view in the UK. This telephone has too many shortcomings to be seriously considered as a means of communication. The device is inherently of no value to us, said Western Union. Or in the UK, the Americans have the need of a telephone, but we do not. We have plenty of messenger boys. Okay. Nonetheless, of course, it did take off. And here's a picture, earlier part of the 20th century, radio telephony around the world, from London, of course, which was the center of the world at the time. But technology moved on apace, and I'm going to move that slider very quickly further forward to 1966, where two people working at Standard Telecommunications Laboratories in Harlow proposed that optical fibres could be used to carry telecommunications signals. And that was the start of the optical fibre resolution. Relatively recently, late in the day, to be regretted, Charles Kao won the Nobel Prize for Physics for that work. George Hockham co-authored the paper with him on that. Where does it go? Well, from my own work, where this went, was under the sea. Submarine telecommunications doesn't mean communicating with submarines, it means telecommunications under the sea. The first transatlantic telegraph cable was laid in 1858. We had to wait almost 100 years for the first transatlantic telephone cable. Before 1956, telephone communications with the United States was via just 12 high-frequency radio channels and depended on the propagation, atmospheric conditions, and so on. When the first transatlantic telephone cable in, it provided 36 simultaneous telephone circuits. There were those who took the view that this was profligacy beyond belief. You would never need 36 simultaneous telephone calls to the United States. They might have been casting aspersions about how many Americans there were worth speaking to, who knows, but nonetheless. I came into work on this with getting optical fibres into this, and we put the first transatlantic telegraph cable in 1988. Since then, it's moved apace. The last project of this nature that I worked on used wavelength division multiplexing, lots and lots and lots of different colors of light, very closely spaced together, with more and more signals on each of these. For those that do it, we were transmitting 40 gigabits per second over each wavelength and had over 100 wavelengths. For those that don't know what that means, I'll interpret it for you. It's a lot. Huge capacity on these. How do we do that? Well, one thing was by using all these different colors. But we use something else as well. And I'm going to take you back to around about 1830 in France, in Paris, to Évariste Galois. Évariste Galois was a young mathematician, around about 21, who died in a duel. And the night before that duel, he sat up scribbling all his ideas, trying to get them down on paper, and laid the foundations for Galois theory, a branch of mathematics. His interest in that, and the interest at the time, was in fact in the solution of equations by radicals. But today, two very important uses of that mathematics are, it's the basis of error control coding, which is how we've got these optical fiber systems operating as they are. It's also part of the groundwork for cryptography. So data security, data coding. The graphs merely show, well, to those that know, they show the power of error control coding. In fact, on those systems, we're transmitting individual bits of data, and at the other end, 1 in 16 of those are in error. But such is the power of the codes that we're using that those errors can be corrected down to better than 1 in 1,000 million. In other words, essentially error-free. And that's the power of the mathematics, and a lot that's come since, that was done in 1830. So research, it's a bit like George Porter, chemistry, applied chemistry, and yet to be applied. The same with mathematics, it finds its place in different ways. Frontier research, there are frontiers everywhere. Some are applied, and some are, there is something here to be studied that will add to knowledge. Another kind of coding is this. On the left is a picture of a young woman. On the right is a wireframe model that models the shape of her face. And back at BT Laboratories, in the days that Rick referred to, we were looking at this. How can we get images down the very limited capacity of a standard telephone line? And one of the ways was to do this. Send the image once. And then just send the small amount of data that represents the points on this wireframe, and at the other end, electronically stick one on the other. I have a suspicion I can't show you the video, so I won't try. But the power of that is really quite remarkable. Today, at that time it was curiosity and might be useful. Today, it's actually in your mobile phone. It's part of what is used in that coding scheme. But imagine that we wanted to code both audio and video together. This is how we would do it. Into 2 telephone circuits. For those that know, these are 64 kilobits per second. We'd code the audio in one and the video in another. And then at the far end, they're presented and put together. So now I want to do this experiment with you that we did again at BT Labs. We've coded the image and we've coded the audio. We send them over the channel. I present them to an eminent individual sitting in the front row. But I've got a trick. I have a cleverer way in which I can code that audio and get better quality out of it. It's called something ADPCM, but that doesn't matter. The important thing is, in the same capacity, I can present you with a better picture. So I do that, and then I say, Rick, did you notice a change? And this is what happens when you ask people. They say, yes. What changed? Sorry, I said it wrong. I can code the audio to give a better audio quality. But when I change that, the perception is that the picture got better. That's a really curious thing. So we improved the audio, but the belief was the picture got better. That tells us something about the way our senses work, about the way we perceive things. We're perceiving both together and constructing a whole. You were conscious that the picture was bad. You weren't so conscious of the imperfections in the audio. When we improved it, the experience improved. And that, as I say, it's a matter of perception, and that's an example, a simple example, of what is called perceptual coding. To address issues like this, think not just about the fidelity of the individual stimuli, but you have to think about how the individual responds to the whole. If you want an example of research that requires people from different disciplines to come together, this has to be it. Telecommunications and signal processing and computing techniques meet perceptual psychologists, and without both of those and the understanding of the brain and the way it works, we won't move that forward as fast as it is. I'm now going to show you another significant event from my past. This was an advertisement that appeared in the Daily Mail, I think, but let's say all the press. And it was for a concert to be given by a famous pop singer of the day, Tina Turner. And Pepsi wanted to do a promotion of their fizzy drink. So they decided to run a competition. Tina Turner was coming to give concerts, and they decided to give away 200 pairs of tickets free to people to go to Tina Turner's concert. The way it worked was this. You bought a can or of Pepsi, you looked at the barcode, you extracted 2 of those numbers and inserted them into a telephone number they'd given you that had 2 question marks. Replace those question marks by these digits and then call the number and we'll give you free tickets. We'll do this on Tuesday evening between 6 o'clock and 7 o'clock. Now I have to give you a bit more information on this. At the time, in Oswestry was the BT Global Network Management Centre, where we could see the state of the BT network at any point around the globe, and specifically in the UK. What we found on that screen at 1 minute to 6 with regard to the Bristol Exchange was, it showed us green lines, everything is fine, everything's working well. And as soon as it tipped past 6 o'clock, that's what happened. All the lines into the Bristol Exchange went red, saying no telecommunications traffic is going through. Panic in Oswestry, we think something's happened to the Bristol Exchange, it seems to have all gone offline and so on. They knew nothing about the Tina Turner promotion. In fact, in 15 minutes after 6 o'clock, this is what happened. There were 50 successful calls to those telephone numbers for Tina Turner concert tickets. And if you remember, they were going to give away 200 pairs. Then they'd got their dimensioning smack on, absolutely right. They were going to get rid of 200 tickets in that time. But in the same 15 minutes, there were 200,000 lost calls. And most of those were not trying to get to a Tina Turner concert. They were real business. In fact, BT, after that, introduced a new capability into their system, which was they employed a new member of staff whose job it was to look through all the national and regional newspapers to try and spot these sort of things so that they could know in advance. I have to say, the engineers responded brilliantly, and in 15 minutes we'd found the problem and put in something that was available to get it right. But it kind of brings up the fact the network needs to know a bit more, and it needs to be responsive. Now let me take you to the Research Council. At about that time, the Science and Engineering Research Council had a subcommittee called the Communications Subcommittee that had just decided to have a specially promoted program on multi-service networks. Instead of thinking just about telecommunication links and exchanges, think in terms of the whole network and the ways in which you manage traffic flows and the behaviors that come there. Really quite advanced for its day. The internet existed, certainly didn't have the prominence it has today. The web had not been invented. The web was invented a bit later, probably a couple of years later, and really came into prominence in the 1990s. So I thought I'd just acknowledge a few people. Tim Berners-Lee is, of course, well known as the inventor of the web. Vint Cerf and Bob Kahn as the fathers, in some sense, of the internet, but they're Americans, so they don't count. The real father of the internet I share with you this evening. Donald Davis of the National Physical Laboratory invented packet switching. And without packet switching, none of this would have come about. So let's tip our cap to Don, because that was the basis for multi-service networking as we implement it today. And it's important because technology is important, but it's not all important. Policy and regulation feature as well. This is Alan Rudge, who at the time was Deputy Chief Executive of BT and the President of the IEE. In his inaugural address, he said, "Technology provides the basis for the future of telecommunications. The exploitation of that technology depends on how the activities of the various players in the market are controlled. Not just technology, but the way we regulate or the way the market operates will feature." In fact, I would say, think in terms of three things: technology, regulation, and competition, a competitive market. And to some extent, regulation is seen as about making sure we have an appropriately competitive market. But it's really important that we don't only have competition. You also need cooperation here. This is the Network Interoperability Consultative Committee, NIACC standards that Rick referred to in the introduction. It's the technical forum in the UK that makes sure that the services that are provided by one telecommunications provider will interoperate with the network of another, that you can start your call on Vodafone and terminate it on Cellnet, or indeed on BT's main network, or whatever. If you think about it, that has to happen. And that means you need a combination of both competition and cooperation. The portmanteau word for that that's sometimes used is co-opetition. Organizations need to learn how to do this and how to change with time. So I want to share with you some work that the Institution of Engineering Technology has just done and just published. And for those in the telecoms field, I'd encourage you to go to the website and look at this. It's a conception of something called demand-attentive networks. If you think of the internet as we use it, certainly as we use it at home, it's never enough, is it? You know, we have broadband. Well, I live in the country. It's limited. And applications just demand more, particularly if you want it to be wireless, where we're limited by spectrum. So this is an attempt to move us from a situation where there's never enough, where there's always sufficient. Notice not infinite bandwidth, just always sufficient, appropriate to the application that one is operating. And it's a good document. I would recommend it. It does seem to me that demand attentiveness of networks is something to work with. But networks are pervasive. Not just telecommunications, but food webs, power networks, and so on. And there's much growth for cross-fertilization in that. This was an experience we had some years ago in the United States, where there was a power failure up on the border with Canada, and it rattled all the way down and hit us right the way down through New Jersey and so on. The network just shut down. And it was literally, I think, a software fault that caused that. That says that we really need to do a lot more on network monitoring and control, and we are, similar to the multi-service networks of telecommunications. In fact, it's the intelligent grid architecture that we need even more as we mix the different sources of energy that we adopt. Another kind of network you'll encounter are called ad hoc. And if you look at this, terminal A, its range is such that it can reach terminal B, but not C. But of course, it could communicate with C. If there was cooperation, it would send its signal to B that would then send it on to C. And that's an ad hoc network that they do that as they move around, and that's a domain that we work in wireless communications today. I thought we would have a look at a transdisciplinary example of that. Starlings, swarming. If you've ever seen them in the night sky, it's quite amazing the way they work. Relatively recent research has found that how this works is that a starling tracks the nearest 7 others, literally just that. It just keeps track of 7 others, and that is sufficient to keep the whole swarm together. If a predator comes in, you'll see the swarm moves away. So that's an area where we can learn from nature, and do. And here's another area of learning. A few years ago, someone asked this question about the World Wide Web. If you think of those links that we click on, actually they form a network. You click on a link, it takes you somewhere else. I wonder what sort of network that is. It could be hierarchical, there are various ways it could be structured. When it was looked at, it was found, it wasn't a random network. It was something that is called scale-free. Now, I'm not going to go into what the details of what scale-free is, but that was quite a remarkable finding with all sorts of implications. When it was studied further, it was found that these scale-free networks, for what they're worth, apply to the internet, to the World Wide Web, to power grids, to aspects of stock markets, to social networks, and to the spread of diseases. And that paper, in a computer science-y type of area, in an informatics area, had an impact on epidemiology. And it's quite complicated. Here's a complicated system, a complex system, if you like. In that square, I have an honest face, so you believe me, there are 400 little dots. So to describe those, each with an X and Y coordinate, I need 800 numbers, and I would have then a description of that state. But I want you to now look at how I really constructed that. I took this grid, rotated it a few times, and then cut it through. So there were 4 numbers really, together a little bit of description. That was an example of something that looked very complex, but looked at in the right way, there was underlying hidden simplicity. Of course, sometimes it's the other way around. And the example I want to give you for that is Langton's ant. This is a computer model, but I want you to think of a grid with an ant placed on it, but this is a strange ant. As it leaves the square, it changes the color from black to white. If it's on a white square, it turns 90 degrees and moves forward. If it's on a black square, it does it the other way. But as it leaves, it inverts the color. And this is what it looks like. So as it paces around, it paces a pattern something like this. And after some number of steps, 386 steps, it's painted that pattern. But if we leave it to run, it wanders around, and then you see a highway emerging. And it will stay in that pattern. Just that highway will grow and grow and grow. This is an example of something called emergence, a characteristic of complex systems. And I think the phrase, be afraid, be very afraid. Because that was a pretty simple thing that I described, and yet it has this enormously complex behavior. Why do I mention it? Think software. If we don't use good formal methods to design software systems, then unexpected emergent phenomena are something that we will have to cope with. And it applies to complex diseases. We need to study those appropriately, and that brings us to the information, knowledge, and wisdom. T.S. Eliot, where is the life we've lost in living? Where is the wisdom we've lost in knowledge? Where is the knowledge we've lost in information? He didn't say the information we've lost in data, but this does speak in some sense to big data, doesn't it? Large data sets from which we can extract knowledge if we go about it in the right way. And that's one of those 8 great technologies that will have an impact. So it's a new frontier that's being addressed. And then to some extent, big data is a new paradigm for doing research. We get it in bioinformatics, where using computing, we can generate huge amounts of bioinformatics data. One example of that is genome sequencing. And I show this slide for a particular reason. This is the cost of sequencing a genome. Notice how it's fallen in the last few years, because we can sequence so much more at once. If we don't have the right equipment, today's equipment, then there are areas of science that are not open to us. One of the things I've been keen to address in my job is that we will get funding for keeping laboratories really up to up to date with modern technology. And that speaks to the life sciences interfacing with the physical sciences. It's worth noting what was said by Harold Varmus, head of the National Institutes of Health in the United States. Medical advances may seem like wizardry, but pull back the curtain and sitting at the lever is a physicist, a chemist, or an engineer. Very powerful, saying we need to work together. And this is an example, again from my own experience. This was at UCL. A colleague was working on biosensors and said, John, will you come and help us with the maths with his student? And I said to Sarah, Sarah, I recognize this. It's a telephone exchange. She looked at me as if I was mad, understandably. But what I'd observed was that the mathematics that we needed to model the performance of that biosensor was precisely the same mathematics that we used to model the performance of telephone exchanges. A really very fruitful cross-collaboration. And the interface between medicine and telecommunications and informatics is growing all the time. My friend Alexander Graham Bell, the inventor of the telephone, knew something about this. Great discoveries and improvements invariably involve the collaboration of many minds. And it's true, isn't it? It's the power of partnership, very much what we need to do. Let's have another nice quote, because I like Samuel Johnson. The chains of habit, too weak to be felt until they're too strong to be broken. I think we've suffered from that a bit in science by being too rigid in our stovepipes, and it's opening out now. That's good to see. But I want to talk about being adventurous, what is sometimes called high risk, high potential return. And I'm addressing now the peer review system that we use to judge science. Negative refraction was highly contentious around 2000, 2002. John Pendry at Imperial College had brought out the mathematics of this and was devastatingly effective in addressing the questions that came. And today, it's absolutely the basis of a lot of new work, including cloaking that we read about, almost Harry Potter there. Antigravity has been on the science agenda since H.G. Wells in some sense, but more in the science fiction agenda. But there is, in fact, at least two bits of work that suggest that that may be possible. There's a current experiment at CERN, which, if successful, is in a sense anti-gravity. If I'd put a proposal into SERC, I know what would have happened to it. In fact, I wrote a paper on this for the Academy some years ago, which I called Risk, Adventure, and the Tyranny of Peer Review. Let's be clear, peer review has served us well. It's very good indeed. The phrase is, it may not be perfect, but it's better than anything else we've come up with. We use it to judge research proposals, we use it to judge papers. And Samuel Johnson, again, had something to say about peer review. Someone sent him a manuscript to look at. He said, your manuscript is both good and original. But went on to say, but the part that is good is not original, and the part that is original is not good. Oh, dear. But the reason I mention peer review is captured here. New horizons aren't discovered by following old roads. So we do need some flexibility in our system to allow people to break out from the conventional into the different. And I think, in principle, I shall stop there. I think I've covered the ground broadly that I wanted to. But I'm conscious that I'm in a very high-level academic institution. So it is appropriate that I should acknowledge my sources, isn't it? And there we are. I've acknowledged my sources. We sometimes say it this way. Copying from one source is plagiarism, but copying from many is researched. Well, it's not true, but at least in that sense, this has been very widely researched. Thank you. I'll stop there.